So Michelle, maybe I should let me just share my screen again and make sure everything's advancing. Okay.
Yeah, sure. It's a good idea.
Okay, so you can see it?
Yes, perfect.
Oh, wait, but I'm not advancing, right?
No.
Oh. So let me just try and fix that. Okay, escape here.
So actually, today I'm gonna try a little experiment, and this webinar will be streamed live on YouTube.
Okay, and now let's try this again. Okay, and now it's advancing, right? Great.
Yes, perfect.
Okay, I'm just going to, is it okay if I just leave it sharing or should I stop?
No, sure. You can just leave it there.
Okay, and I had one other question, which is, what about questions? Will you be just monitoring the channel for a raised hand, or how do we do that?
Right. So usually we have a session then for questions, like 10 minutes or so.
Okay.
But if people have questions in the meantime, I'll be monitoring the chat as well.
Okay. And can you see my little cursor as I move it around?
Yes.
Good. Okay. Terrific.
Okay, so let's just wait a minute or two for the latecomers, and then we'll start.
Okay.
All right, I think we can start now. So hello, everyone. Thank you for coming. Today, we're going to have Kovacs from Argonne talking to us about the DC2 simulation. So thank you very much, Eve, for accepting our invite for this webinar. And whenever you're ready.
Yeah, well, thank you very much for inviting me. So today I'm going to tell you about the work we did simulating basically a mock sky catalog for the LSST DESC science collaboration. And this was a work, in fact, done by a huge number of people. And you can see the list of names of the Argonne team underneath the title. And in addition, there was also a lot of input from Yao Yuan Mao and the LSST DESC DC2 validation team. So what I'd like to cover today is to give you a bit of an introduction into why we do these simulations and what we're trying to achieve and what the challenges are. And then go into the actual nuts and bolts of how we build these synthetic skies, starting from the underlying n-body simulations and going through to actually building the sky as an observer would see it. And then finally, I'd like to talk about the catalog validation. And this includes developing validation tests and actually looking at the results to show how well the simulated sky agrees with the real one. So since this is a bit of a general audience and you might not all be survey scientists or dark matter cosmologists, I thought I'd give you a little bit of an introduction about what these simulations are trying to do. And that, of course, is basically forward modeling the entire universe. Now, we know pretty well, we've all seen this picture before, we know pretty well that we start off with some initial density fluctuations that are the seeds of the collapse of objects that become larger and larger as time goes on, and this follows through to the formation of stars and galaxies and eventually clusters of galaxies, and here you're in a highly nonlinear regime. Now we have a model, the lambda CDM model, which has been amazingly successful in describing this behavior, and its ingredients consist of things like the expansion history, that's the change in the scale factor, and the specifications of the underlying density field. And the parameters have been largely determined from CMB experiments. And unfortunately, what we'd like to do is to improve our inferences on these model parameters. We don't really know what's in the model itself. We don't know what's causing it, but we can describe it very well. Now, unfortunately, we can't do first principles calculations of these quantities. Once these density fluctuations become very large, perturbation theory breaks down, and so you have no option but to go to simulations. Further complicating the issue is that when we look out and observe the sky, we don't observe directly the change in the scale factor or the density fields. What we observe are galaxies and other transient objects, and the galaxies are biased traces of this growth of structure of the underlying density field that we really want to understand. And so I hope that that's convinced you that simulations are just absolutely crucial for understanding this nonlinear growth, the observational biases, the fact that we've only got one universe to observe, so we can't go out and repeat the experiment, and things like cosmic variance have to be understood. Okay, so what are the components of the model? Well, the one that we really care about as survey scientists is this dark energy component. And we don't really know what that is, but we model it as this fluid with an equation of state parameter W that describes the ratio of the pressure to the density. And when W is, we think that W is constant, roughly, and approximately equal to -1. And in that case, this density scales like the power of -3 to the 1 plus W. So you see, if W is exactly -1, then what we end up with in the Hubble law is this cosmological constant, because the A dependence completely cancels out. And then this is the thing that drives the accelerated expansion of the universe that we see at small redshifts or late times. So one of the pressing questions that we really want to answer is W indeed a constant, and is its value equal to -1? So that signals the fact that we're actually in an era now of precision cosmology. We've got these large sky surveys, so-called stage 3 surveys such as DES that are completing now, and the upcoming stage 4 surveys such as the one at the Rubin Observatory has even bigger area and coverage and more demanding science goals. LSST will image about 18,000 square degrees of the sky. It's going to look very deep in redshift. The R-band magnitudes of the galaxies that will be observed go down to about 27. This is billions of galaxies. So the statistical errors will be tiny and the systematic errors will dominate. So on the right here, I'm showing you a plot of the projected change in the uncertainties as we go from stage 3 in red through to the combined analyses in a stage 4 experiment in this tiny black contour. This is in the W0 WA plane where I've now parameterized W as a constant piece W0 and a scale dependent piece WA. And so this shows that the expected precision will really shrink, and the expected uncertainty will really shrink as we complete the 10-year stage 4 analyses. And so again, this should underscore the need for not only simulations, but large volume simulations. And to understand all of the science, they need to have high fidelity and produce realistic mock skies. And so how will this catalog that we produce be used? And it's going to be used in a lot of different diverse ways. And one of the principal ones is to generate image simulations. So the CosmoDC2 was in fact used as the extragalactic catalog that was the input to the image simulation pipeline to subsequently produce real images, which were then put through the data management processing pipeline and to produce the images, simulated images that the various analysis groups could use. And they can subsequently design their analyses and do systematics calibration. This catalog can also be used to test photometric redshift estimation codes, to test pipelines, and to design surveys. So all of these diverse uses of the catalog means that the simulated sky has to not only be realistic, but it has to supply a very wide range of galaxy properties. And this is a very demanding criterion. So how do we go about doing this? So we're now on to how this is now the cookbook for how to build a synthetic sky. And CosmoDC2 is based on an Argonne ANL simulation called the Outer Rim. This is a gravity-only simulation. It's a very large box. It's 4.225 GPC on one side. There's over 1 trillion tracer particles. The particle mass is about 2 by 10 to the 9 solar masses. And so this is one of the largest simulations available with this particle resolution. It's based on WMAP7 cosmology. Altogether, it generated over 5 petabytes of data. So I'm showing you a visualization of the outer rim box here. And these spheres are the halos, the dark matter halos, above about 2 by 10 to the 15. And so there's 1,000 or so of these objects, which is a very large number of these very massive halos. Now you might wonder, well, if we really want to get the physics right, don't we have to include all of the gas physics, the so-called gastrophysics, and shouldn't we be doing a hydrodynamical simulation? And the problem is that at the moment, these are just too expensive to run at such a large scale. And so it can't be done yet, maybe in the future. Now, the way these n-body simulations proceed is to run through a series of snapshots. They evolve forward in time, and as you go forward to smaller redshifts, you get more and more clustering of galaxies. This is the the dark matter, by the way, these aren't galaxies, right? These light, although they look like galaxies, they're not. This is tracing the structure, evolution of the dark matter. And you see the halos forming in clusters and so on. And we have 101 snapshots from Z of 10 to Z of 0, and they're evenly spaced in log A, and these are saved. Full particle outputs and 1% downsampled outputs are saved. A halo catalog is generated by running an FO Friends of Friends halo finder with a linking length of 0.168. And there has to be at least 20 particles in the halo for the halo to be found. We also generate what are called halo merger trees. And these are basically tracking the mass assembly of a particular halo. So you identify a halo, it's equals 0, and you can go backward in time and figure out all of its progenitors and work out what its mass assembly history is. And this backwards in time processing actually removes a problematic issue where the paradigm of a merger tree is that halos should not split as you go forward in time. And using this backwards evolution gets around that problem. We also ran a smaller companion simulation called Alpha Q, and that was on a 360 MPC cube box. And that was used for prototyping this whole catalog pipeline, and also for running a portion of the galaxy formation model that we use to populate the halos with galaxies. So now I've just finished telling you that the simulation proceeds in snapshots, but when we go out and observe, we don't observe snapshots, we observe a light cone. So what we see as observers are the objects that were on our light cone. And so from the snapshots, we build particle and halo light cones. And the particle light cones are actually the basis for computing all of the weak lensing quantities, and I'll be talking about that in a few slides. And the halo light cones that we generate are going to be populated with galaxies, and this is what builds the mock sky. And the way the light cone is built is to look out on the observer's null geodesic and to look for objects that pass through the light cone. It could be that it just happens to intersect with one of the snapshots, but most likely the object passed the observer's light cone sometime between the snapshot, and you just use linear interpolation to figure out where that was. Now, those of you who know your cosmological distances will immediately realize that if we want to go out to redshift 3, this is a distance of about 6 GPC, and that's bigger than the box that we have. And so what you do in those cases is you replicate the box, and you also use some reflection to prevent the repeated structures happening along the line of sight. And one other point I'd like to make is that the merger trees that we built on the previous slide are actually critical for building halo light cones, because we have to be able to know that halo H came from its halo MMP in this diagram. This is its most massive progenitor. And that's how we tell when the halo crossed the light cone. And we just again use this linear interpolation to find H prime. The properties that we give to H prime are actually just the properties of H. It's just a choice. You have to choose one or the other. You could choose to interpolate the properties, but that doesn't really make much difference. So we just choose to use the properties at H. Okay, so here's a summary of the simulation products that are the ingredients for the next step, which is to actually put in the galaxies. And I've just finished telling you the outer rim simulation products are the particle light cones and the halo light cones. And then the smaller companion simulation products are these alpha Q halo merger trees. And so down here, these are now the ingredients that go into the next step. So what is the next step? Well, that's to model the galaxy halo connection. So we have our halo catalog, and we need to figure out some kind of model to populate these halos with galaxies. Now, there's a couple of different ways to do this. The first is empirical models. And what you're doing here is actually making some model and trying to fit the empirical data. For example, your empirical data could be the stellar mass function at a variety of different redshifts. And so there are these various models around, and they vary in complexity. The acronyms are HOD for Halo Occupation Distribution, and this is just a simple model that simply paints galaxies onto halos and tries to get the number of galaxies in the halo of a given mass correctly, and it tunes to observational data to do that. Another one is SHAM, which is subhalo abundance matching. And in this case, you identify some property of the halo, such as its mass, and try to match it directly onto some observable properties, such as stellar mass, and adjust the model so that you actually copy the galaxy properties into that halo. And then there are somewhat more complicated models, and one example of that is Universe Machine, and that's actually the one we used. And this actually Universe Machine makes a model for the stellar mass and the star formation rate, and then does a huge MCMC. So it makes a model actually for the star formation rate, and then it integrates that rate to figure out the stellar mass at any particular redshift. And it populates the halos with galaxies, and it fits things like the stellar mass distribution and other observable quantities. It's a big MCMC. The paper here describes that in detail. But what you need to know about this is that for a start, the galaxy properties that you assign will only be statistically correct, because you don't actually do an overall fit to each halo. You're just doing an overall fit to the distributions. And really only a limited set of properties can be determined this way. And so the possible correlations between properties might be lost in this procedure. Now, another way of modeling the galaxy halo connection is to use a semi-analytic model. Now, this is where the use of a merger tree comes in, because the semi-analytic models accept these merger trees as inputs. So this is a diagram of a halo merger tree, and the small halo down at the bottom here is the halo at Z, the parent halo at Z equals 0. And as you go back in time, you can see all of the halos that contributed to the final mass of this object, and they're color-coded so that the slightly blue colors, I hope nobody's read blue colorblind, because they will not be able to see the difference on this diagram. But this slightly bluer branch is the main progenitor branch of this halo. Now, what semi-analytic models do is they have a set of coupled ordinary differential equations that track each galaxy's mass assembly history, and they model the growth of stars. They model the growth of the luminosity that's coupled to the growth of the stars. And so they try to actually individually determine what the stellar mass content and resulting other properties of each galaxy is. And so they get an assembly of ellipticals and spirals and so on, depending on the specific mass assembly history of each galaxy. Now, as you might imagine, these are much more expensive to run, and there's really a lot of parameters underlying all of these models, because you have to have a model for how the star formation, how the halo mass relates to the gas mass, which in turn relates to the stellar mass, and so on. And so these parameters are actually, unfortunately, mass resolution dependent on the simulation. And so they have to be, in principle, they'd have to be tuned for each specific simulation. And so that's also a very expensive process. At the time when we started building this catalog, the only publicly available semi-analytic model was Galacticus, and that's the one we use. That's actually quite, although it's very agnostic in that it doesn't try to model a lot of things. It really tries to do everything as much as it can from first principles, and that makes it extra expensive and slow to run. And so it became very clear that it was not feasible to run this on the whole outer ring. We did, however, run it on the smaller simulation. And so how did we leverage what we had? So for CosmoDC2, What we actually did was to introduce a new hybrid method that combines both these empirical and semi-analytic methods. And we used resampling techniques to populate a large simulation with these realistically complex galaxies. So the empirical model that we used was Universe Machine, which was tuned on a smaller simulation, and it established the galaxy halo connections just for a very limited set of properties. And those were the stellar mass, the star formation rate. And we did a little bit of additional modeling, which I'll describe in a moment. The galaxies from this small simulation, the Universe Machine, are resampled into the larger simulation. And so here we are with our overall workflow. We have our outer rim simulation products, we have our Universe Machine, and we have our Alpha Q. The Universe Machine was used to populate the dark matter halos with these empirically modeled determined galaxies to make what we called the base DC2 catalog. The outer rim simulation was also used to make the weak lensing quantities, which made some lensing maps. I'll be talking about that in a few slides. And the Alpha Q was run through the SAM and made a library of galaxies that we could use. This expensive for augmenting the properties that we wanted to include. So the galaxy properties obtained from the small simulation using this Galacticus semi-analytic model are used as a library. This semi-analytic modeling is run once without any special tuning. And what we do is we match up the galaxies in this empirical model here with galaxies from the library and use those to populate, to fill out all of the properties. Okay, so that's the overall workflow. Now, the empirical model pipeline was based on, as I said, based on Universe Machine with realistic distributions of M star, stellar mass, and star formation rates. And we match the halos in outer rim by mass to the Universe Machine halos, and then we resample the galaxy content of the Universe Machine halo into the matching outer rim halo. And this is described in a paper called Gal Sampler, which is linked here. Additionally, we have to augment the modeling by adding some flux modeling for the rest frame, for selected rest frame LSST filters. And this is done so we can then do the matching to get the more complex properties. This model augmentation is now based on the stellar mass and star formation rates that we have already obtained from the Universe Machine. So we've resampled Universe Machine, got these galaxies with the very limited properties. We're adding some rest frame colors and magnitudes. Since there's one point that's worth mentioning here, since the Universe Machine was coming from a smaller simulation, there will be some missing very high mass halos. And so we had to come up with a way to boost the stellar mass of the central objects and the number of satellites for these very high mass halos. So that's all of these details were just described in the CosmoDC2 paper, and I'll refer you to that for more details. Another important point to note is that we had to add some ultra faint galaxies. This is now compensating for the mass resolution of the simulation. Remember that our particle mass was 10 to the 9, our lowest halo mass is just under 10 to the 11. And so this meant that we did not have sufficiently small mass halos in the simulation to make these very, very faint galaxies that will be seen by LSST. And so we had to compensate for that. And again, the details of that modeling are described in the paper. So now I'm going to go on and talk about how we did the weak lensing. And just to remind you that images of distant galaxies will be distorted due to weak gravitational lensing, which just describes the series of deflections that happen as the light between us and the distant source passes by large structure. So you have a cluster in this lens plane here that's doing the lensing. You have the background galaxies on the source plane. And so here's an example of the kind, the magnification and the tangential shear. This is the distortion of the galaxy shape that you observe around, from light coming past a massive cluster in the intervening, along the intervening line of sight. So here's the weak lensing pipeline that we used for CosmoDC2. And what we do is we divide this downsampled particle light cones into shells roughly 114 mpc wide. And we estimate the surface densities on each of these shells by dividing it into a Hill-Pix grid with n side equal to 4096, which is roughly arc-minute scale. Once you've got these surface mass densities, you can do ray tracing to compute the distortions, the deflections, and produce lensing maps. And this is all done on an observer grid. And so again, technical detail that's described in the paper, but you have to shift the galaxies, then shift the galaxies to their observed positions, and then you assign the lensing quantities, the shear and the magnifications by interpolation on those resulting positions. So just to show you how that looks, this is underlying here is a density map of a 100 square degree patch at around Z of 1. And then this tiny corner is blown up to show you overlaid the lensing map and the shear around shear map that lies on top of this. And you can see how the shear is aligned with the massive structure. So now with the lensing and the baseline catalog, we're now ready to fill out all that huge host of properties that we need to add to make it a realistic catalog. We have to start with so we're starting with the lensing map and this empirically modeled catalog and the Galacticus library. And I've just described to you adding in the weak lensing pieces. And now we have to do this big matchup where we match the properties in the base DC2 catalog with the Galacticus library properties and fill out all of the other properties by copying the properties from the matched galaxy. So what we want to do is preserve the careful tuning of the original empirical model, but augment it with the properties from additional information from the SAM library. So what we do is to match the R band magnitudes in G minus R and R minus I colors with those of the Galacticus library galaxies. Now there's a little bit of a technical problem here in that the Galacticus library is run again on snapshots because it was run on the merger trees, and the merger trees only exist at various snapshots. And so if we just go ahead and match with the nearest snapshot, we get all kinds of nasty discreteness effects that come from the fact that we don't have enough finely sampled snapshots. So what we did to get around that was we interpolated the library galaxies between snapshots to minimize those discreteness effects. And so that's all of these pieces here where we interpret like the library, and we also have to divide to do this matchup. We use KDE trees, and so it's also necessary to look at shells of light cones to do this matchup in the most efficient way, because we can't afford to construct a KDE tree for the redshift of every galaxy. That's too time consuming. So the KDE tree is done by, the matchup is done by finding the nearest neighbors that minimize the Euclidean distance in these quantities, and we randomly select from the 10 nearest neighbors so that we're not inadvertently resampling the same galaxy over and over again in regions where you don't have a lot of dense population. There's another special little feature that's done for galaxies on the red sequence. those are also required to match the observed DES red sequence. And this is a special step done that makes sure that we have a sufficiently well-defined red sequence in cluster members to allow RedMapper to actually run, which is an optical, RedMapper is an optical cluster finder that's used extensively, and it's very important for the cluster working group to have that capability. Once we've got all of the augmented properties that include disk and bulge properties and other things that we all got from the SAM, we do a little bit of additional empirical modeling based on some of those quantities for galaxy shapes and sizes. So that's the whole, oops, what happened to my, uh-oh. You don't see me advancing, do you?
No.
Okay, and I'm going to, sorry, technical glitch. I think I'm going to have to stop share and get out of this and start again. So sorry, let me do that. Okay, where's my? And how about that? Are we back?
Yes, yes, perfect.
Yes, now we're advancing. I guess I took too long on one slide. It forgot. Okay, so here's an example of how this matchup looks. What I'm showing you are 1D and 2D, 1D color distribution and a 2D magnitude and color distribution. And in blue, you see the underlying distribution of so what we call the base DC2 catalog, so the empirical model. And in orange, you see the distribution that comes from the Galacticus library. And then in green, you see the outcome of doing this KDE tree matching that I just talked about. So you can see that the overlap is really good. We basically are ignoring library galaxies that don't match with what we want. And so in that way, we're effectively retuning the semi-analytic model. One thing to note here is that there is a couple of little spots where we don't have any Galacticus libraries to match the properties that we want. And the way we try to mitigate this is by doing an adjustment on the matching criteria, and we down-weighted the luminosity matching in favor of color. So we did manage to extend our reach, as it were, into this region where we in principle didn't have any Galacticus galaxies. And then we just retuned the luminosity to match what we wanted. So now, after all of that, we finally have a CosmoDC2 catalog. It's 440 square degrees. It goes out to a redshift of 3. It's complete down to an R-band magnitude of 28. It has a wide range of galaxy properties, including stellar mass, UGRI-ZY rest and observer frame magnitudes, galaxy shapes and sizes, weak lensing. It's delivered in HealPix format. Each HealPix is about 3.4 square degrees. And a full description of everything can be found in the CosmoDC2 paper, which is linked here. So on to catalog validation. Now, this whole production pipeline was accompanied by an extensive validation effort that ran alongside this production. And so I want to go into the aims of the validation process, how we design these validation and verification tests, the validation data that we used, how we actually ran the validation, and then show you some results. So why are we doing this validation? Well, so far I've been talking about CosmoDC2 production, and basically the steps that I've shown you are outlined in this little red box here. This catalog was then used as the input for image simulations. And so the rest of that pipeline is shown on this slide, where you take the catalog and put it through an image simulation, you run it through the DM stack, the data management stack, and you produce the output catalog that's going to be like what we get from Rubin when we do the observations. So this is a huge pipeline. It's an end-to-end pipeline. It requires a huge investment of computer time, of human resources. And we have to make sure that the things that we put into this are actually capturing the physics we want to include, and that the level of complexity that we have is sufficiently realistic and sufficiently complex for the intended science use cases. One distinction that you have to make when doing verification and validation is the fact that verification is really about checking to see if the things that you've included are actually being included correctly. So are you building the product correctly? Validation is really far more involved, and that means, are we building the correct product? Are we really putting in things that are needed, and do we have the details correct? And both kinds of these tests were done on CosmoDC2. So validation tests are actually quite a complex issue, and designing them is not so trivial. There are multiple science use cases for these catalogs. I've already mentioned some of these before: the image simulations, photo-Z algorithms. Testing galaxy deblending is a particularly important one. Testing systematics for analysis. So you have to ask then, what galaxy properties have to be rendered correctly? And that means one example of that would be galaxy number densities are very important. And you expect those have to be correct for a number of reasons, and I'll get to that in a moment. And then, what does correct even mean? What level of agreement do you need between the catalog and the observational data to meet the science objectives? And so this suite of validation tests really give you quantitative measures that allow you to assess the level of realism provided by a catalog, and in fact to determine how a catalog can be used. A very important part of this step is curating the validation data. You have to take stock of what the available data is and decide on what the best data set is to use, and whether you can combine data sets to get what you need. And one example of this is number density tests, where you need number counts from a survey that is really wide, because you don't want cosmic variance to play a big role, but also very deep. And that's because you need to find faint objects, and wide and deep surveys are hard to come by. Furthermore, you have to understand what selections have been made on the data set that you're using. For example, magnitude flux selections, redshift ranges, and so on, and whether you can replicate those selections in the simulated data. And that means that, you know, if they cut on galaxy morphology, well, there are various complicated algorithms to decide on morphology. How do you implement those cuts? Can you implement them directly? Redshift, yes, you could. Galaxy morphology, it's more complicated. And so sometimes, in some cases, you have to find a proxy to try and mark up the selection effect to see how well you're doing. Next is how do we actually run these validation tests? And in DESCQA, we've developed this, in DESC rather, we've developed this validation framework called DESCQA. And this is a nice generalized framework that allows you to run a bunch of tests on a bunch of catalogs. And so there's a schematic of how that works here. And there's a master execution script, and you tell it which catalogs you want to run on. There's a reader interface that reads the different catalogs. And then you tell it which test you want to run. And there's a validation test interface that allows you to pick a bunch of tests. It runs all of this stuff, it outputs on the file system, and then there's a user-facing website that talks to these interface scripts and displays the results. And this is on demand. Basically, you run the test and then the user can go and look at the test results. All of this is documented. There's a couple of GitHub repositories that I've put links to for the code. And there's a DESCQA paper that's also linked here that describes this framework, but it's very convenient. The nice thing about the catalog reader is that the catalog producers all like to use their own formats. And having a reader here basically homogenizes all the different formats of all the different catalogs and puts them all into the same thing so that the test doesn't have to distinguish between the catalogs that it runs on. It just uses the same code. And although this GCR concept was done initially for the DESCQA interface, it's actually now widely used in LSST Desk because people find it very convenient. They can play with different catalogs, different simulated catalogs, and even the ones that are produced by from the image sims all work with this GCR reader, and the same code runs on your catalog regardless of where it comes from. So it's very nice. Here's an example of a DESCQA summary page. Here is the matrix of the tests and the catalogs, and then it outputs this matrix. Each test produces plots of the catalog and validation data, and it delivers a status on optional scores. Not all of them have scores. These are the so-called validation criteria, and then there can be a pass or a fail, which we've softened to be not quite. I'll give you some more examples of this in a couple of moments. And don't get scared when you see this page. This is an example of the CosmoDC2 verification tests that we did. We did a bunch of tests called readiness tests, and these were readiness to run in the image simulations. As I said before, we passed the CosmoDC2 code on to image simulations, and this just checked for things like, were all the variables distributed as we expected them to, and flagged anything that looked a bit funny. And so I don't want to go into too many details here, but it's just, it was a very convenient way to make sure that the things that, quantities that we were feeding to the image simulations weren't going to be a problem. So assembling the validation tests was a lot of work by the different working analysis groups, and it was a strong collaborative effort. What they did was they identified a series of critical galaxy properties that required validation. And different groups had lots of overlap between the different requirements. The critical properties were the galaxy number densities, the 2-point correlation functions, both the projected and the angular, and this included galaxy-galaxy correlations, shear-shear correlations, and galaxy shear cross correlations, galaxy shapes and sizes, galaxies in cluster environments, and the stellar mass function. So I'm going to go ahead and show you some of these tests now. The galaxy number densities were the most important ones. The science drivers for this were large-scale structure and weak lensing. And the reason is that the noise in these measurements goes like 1/n. And so if your galaxy density isn't correct, then your systematics evaluations will be off. And the number density as a function of redshift was very important for tomographic binning. The photo-Zs needed this to assess the accuracy of photo-Z algorithms. They needed to understand the distribution and redshift evolution of SEDs. Blending is obviously important for the number density on the sky is obviously important to assess the accuracy and efficiency of deblending algorithms and for recognizing unrecognized blends, or for evaluating the effects of unrecognized blends. So what we'd really like to do here is to validate number densities of galaxies as a function of redshift and flux in the filter band passes. And this is a complex multi-dimensional space, and it's simply not fully explored by the available data. And so what you have to do is to just consider projections of this space and match to whatever data you have available. And so those tests turned out to be cumulative number densities as a function of magnitude. That tested the absolute normalization. The N of Z distribution for selected magnitude ranges, which tested the shape as a function of redshift. color distributions for selected magnitude and redshift ranges, which tested 1D projections of colors, and then some color and color magnitude distributions, which is just testing full 2D projections. So let me show you a few of those. This is the cumulative number density test. So this is now the cumulative number density. This is the number density per square arc minute, per square degree, I'm sorry, per square degree that's less than the magnitude on the x-axis. The blue line is CosmoDC2. The black line is HSC extrapolated data. So what we had to do here was extrapolate the density, the number densities from the HSC survey, which is a wide survey, and cross-check the numbers with numbers from pencil beam surveys to make sure that the extrapolation at the depths beyond the HSC survey were valid. The validation region that was specified by weak lensing and deep blending was this 24 to 27 region, so very faint galaxies. And the validation criteria was set to be, we wanted to be within plus or minus 40% of the target. So the very faintest galaxies are out here where this red circle is. And this is where it was absolutely crucial to add the ultra faint galaxies to the catalog, because without those, we wouldn't have passed this test. Here is the number density versus redshift test. And this is as a function of different cuts on the R-band magnitude. And so it's the normalized distribution of Z given this magnitude, conditional distribution. And the errors are jackknife errors to account for the cosmic variance. And the data is from deep 2 fitted to observations. So the deep 2 data is fitted to, the distribution is fitted to observation, and that's shown in the dotted black line. And the blue points are the points from CosmoDC2. And the range of validity of those fits is about out to redshift of 1.5. So we have pretty good validation. It's not perfect, but it's reasonable. It's acceptable, I would say. The Photo Z group said it was acceptable, which is more important. Color distributions. So here we have, again, this is the Photo Z group that needs to have this reasonably realistic. And the data was the SDSS GRIZ catalog, and also the Deep 2 catalog. Now, when CosmoDC2 was, when the Alpha Q simulation was run on Galacticus, we not only simulated LSST filter magnitudes, we also simulated SSD magnitudes in anticipation that we would be doing validation against SDSS data. Did I say SSS? Yeah, anyway. And that now comes in very handy because we were able, when we did the matchup, of course, we got those SDSS magnitudes for free. And so we were able to validate the color distributions against SDSS magnitudes without doing any filter transformations. So the smaller plots at the bottom shows how CosmoDC2 in orange compares with SDSS in blue. You'll notice that there's some excess in the red region. This is G minus, these are the 4 U minus G, G minus R, R minus I, I minus C colors. And you'll notice there's, in general, there's some excess in the red. And this is, again, a deliberate tweaking of our empirical model to make sure that there was an abundant red sequence available for red mapper. So you can see that, especially at higher redshifts, there's this excess of red galaxies. Okay, how am I doing on time? Not too badly. Let me show you the correlation functions. These are the so on the top is the angular correlation function for various magnitude cuts compared with SDSS data. And on the bottom is the WPRP, the projected 2-point projected correlation function, which is the projected distance on the sky. So the bottom plot is DIG2 data, and it's based on a stellar mass cut. And it's at redshifts of 0.75 to 1. And so again, you see CosmoDC2, except at the very smallest angular scales, very smallest distance is in very good agreement with the 2-point function. And that says just that the clustering of galaxies is correct. So on to lensing and shear-shear correlations. What I'm showing you on the top plot here, the points are the SDSS low-Z sample for the excess surface mass density. And this quantity delta sigma is basically the average of the tangential shear divided by the critical surface density. And so it measures the correlation between the shear and the distribution of galaxies. And you see that CosmoDC2 is in really good agreement. What's happening here at this fall off is that's due to the pixelization of the weak lensing calculations that I spoke to you about. So that's expected. You can also do some tests that compare the shear-shear correlation function, the two components of it, psi plus and psi minus, which are the two components of the shear-shear autocorrelation. You can do a theoretical calculation based on CAM power spectra, and that that is only valid in a region of larger angular separations. But again, you see that at large distances, it agrees very well within these dotted bands. The other nice thing about this bottom test is that it checks your sign conventions and makes sure that your sign conventions for shear are what you think they are. Let me show you a couple of, in the last couple of minutes, let me show you a couple of galaxy cluster tests. This is the red sequence test. This is on the top is the red sequence for just ordinary galaxies that are labeled red sequence galaxies. In our empirical model, we select whether a galaxy is on the red sequence or not. That just basically says, does it come from the red part of the empirically modeled distribution? If it's in a high mass halo, you see that the scatter on this relationship for the red sequence, which is the color versus redshift, is much tighter. And that's what you need for RedMap, this optical finder, cluster finder, to work well. So you expect this to be good because we did some tuning to make sure it would be good. Other things you can look at are the mass richness relation. And I'll just direct your attention to the red points here, which is the red triangles are the cluster, the CosmoDC2 cluster members with as determined by RedMapper. And these lines and shaded bands are what is observed by DES for the mass richness relation. And similarly for the velocity dispersion as a function of the adjusted halo mass. So both of these tests look pretty good. Some of them need a little bit more tweaking. We have to do some checks on the mass definitions to make sure that we're converting everything correctly, but everything is, these tests are still under some development. Finally, I want to show you the stellar mass function. And this is just a basic test to make sure that everything looks good in the stellar mass. It's kind of the underlying fundamental probe of the galaxy halo connection. It's a check that all of our matching and everything else that we did proceeded as expected. And it's also relevant for supernova science. The data you're seeing here is the Mustakis measurement of the stellar mass function for different redshift slices. I'm going to skip. I've got a couple of tests on size distributions and ellipticity distributions. These were actually modeled additionally on top of the after the matchup, and so we expect them to work, and so there's no real check here other than that we did it correctly. So let me just give you a quick conclusion since I'm in the last couple of minutes. I've shown you a new hybrid method to simulate realistically complex galaxies. It leverages small simulations by resampling the galaxies into a big volume. it runs pretty quickly once everything's tuned, but you can allow some flexibility here so that you can actually make adjustments and retune, and we did that. You could imagine replacing the SAM library by resampling from a hydro simulation, for example. So this would be a way to leverage a hydro simulation if that's what you wanted to do. And the catalog validation I showed you was that we have developed a test suite that's applicable to ground-based imaging surveys that target dark energy science. And we've assembled a set of curated validation data that's relevant for these surveys. It could be extended to other bands, and the test suite could be adapted to other surveys by augmenting the data and adjusting the validation criteria depending on the science goals. So we've got a paper in preparation. And the last slide is just to give you an advertisement that SkySim 5000 is coming soon. This is a 5,000 square degree catalog. We've put in a couple of improvements, but it's basically CosmoDC2 in steroids, and we hope that'll be coming out very soon. So thanks very much for listening. And if you have any questions. Oh, maybe.
All right, thank you very much. Yeah, sure. So questions, please.
I have.
Yeah.
Hi, thank you very much for a fantastic presentation. I mean, first of all, the demand in storage must be huge, right? I mean, from your first slides, you store everything, right? How much do you? Yeah,
the simulation data products are more than 5 petabytes of data. And so a lot of it is stored, it's basically the particle outputs, and those are stored on tape. And then the downsampled particles, which is the 1% downsampling, is stored on disk. And that's what's used for most of the construction of the light cones and so on. The Halo catalogs are not that big. Halo catalogs can be stored on disk. And then CosmoDC2 itself is about 5 terabytes. And that's sitting on disk at NERSC.
And that's it's a 10-year baseline, right, for this DC2?
Yeah, but the 10-year of observations, so if you're asking me the DC2 storage requirements, that's different, right? Because then the extragalactic catalog, in a sense, is only made once, right? But then when they do the image simulations, they do the repeated observations.
Oh, I see.
Different parts of the sky, and so they have to store the observing cadence. And frankly, I'm not quite sure what the storage requirements are for that. But you
do implement a 5-year, 2-year with the errors, magnitude errors and so on, or that's up to the user?
I'm sorry, say that again.
If you do some simulation, you simulate a true catalog, an observer catalog that is with the errors and the magnitude and so on.
Yeah, so CosmoDC2 itself doesn't have, it's the extragalactic part, and it doesn't have the errors.
Okay.
So what's happened with that is that the PhotoZ group have modeled the photometric errors for, I think, the 10-year errors. They have a model for how those will look, and they've produced an add-on catalog that's available in addition that can be added on to CosmoDC2 for the error estimates. And then they've used those in the photometric estimation codes.
Okay. So my last question, I mean, when do you expect to have this 5,000 square degrees?
We're waiting right now. I'm ready to push the button. What we're waiting on is the completion of the weak lensing part. So the area that I showed you was the 5,000 square degrees all ready for the limited set of properties. But that won't make you happy because it doesn't have observer frame magnitudes or anything like that in. So we're all ready to run the matchup pipeline. I've tested it. It works, and we're just waiting on the completion of the weak lensing maps and the shear estimation. Once that's done, we'll start to push the button, and then a couple of weeks after that, I think. So,
tell me, what is the total time investment? I mean, how much time did you guys, the group, invested in these simulations from start to?
Well, I showed, it depends on how far back you want to go, because the underlying n-body simulation is the product of many years of work on something of this scale. It's the culmination of many, many years of work by Katrin and Salman and their simulations group, and they've spent many years developing their code so that its feature is that it's very flexible and can can run on different machines very quickly without rewriting the code. And so they've been able to be very nimble and take advantage of new machines as they come along.
But was that LSST driven, or was it just
that was driven by them, and then that simulation was available, and then several of us worked, I would say a group of 4 or 5 people at Argonne worked on CosmoDC2 for a couple of years.
Fantastic.
Not 100% of the time, but you know, a significant fraction of time for all of us, I think. And then going on and doing the image simulations. And actually what happened was that everything was prototyped, and the image simulation program was running on the prototype catalog. And so we had quite a bit of back and forth with adjustments and changes because it was all happening at once. So,
I can imagine. Yeah. Well, brilliant.
Yeah.
Fantastic. Thank you very much.
Okay, any more questions?
Yep, I have one.
Yes.
Hi, Eva. Very impressive, the work with the simulations. And I have a simple question. I want to perform an analysis in the cluster working group to estimate the mass of clusters. So as I understood, we have in the CosmoDC2 catalog, we have the halos, the galaxies, which belongs the member of that halo, and they shear for each galaxy. Is that right?
Yep.
The photo Z, we also have the photo Z for those galaxies. This last part, that's not so clear for me.
So this is exactly the add-on catalog that I was mentioning to Louise. This is all now nicely available now in this. I mean, are you an LSST desk member?
Yeah, yeah.
Yeah. Okay, so what you have to do is there's actually a page, DC2 product overview, or there's a Confluence page called, under the Cosmology Simulations Working Group, called Proto DC2 and Cosmo DC2 information. That PhotoZ catalog is an add-on, and it's as simple as providing the name of the PhotoZ catalog if you use this GCR reader.
Okay.
It's available, and there's a link to the PhotoZ add-on catalogs page from both of those pages, and you can read about what they are. Sam Schmidt is the person who did that, and that's just recently become available. And they've got PhotoZs for the BPZ algorithm and also for a machine learning algorithm, FlexiBoost. Sorry for the others, this is all jargon, but yeah, basically, I think it'll be very easy to get the PhotoZs now. Should be.
Great. Great.
Yeah.
Oh, that's great. And I don't know, should we...
And there's also a RedMapper catalog.
Okay.
There's also a RedMapper catalog that's just been recently run, also an add-on.
Okay.
So, yep.
Great, great. And do you know if we should announce the analysis that we want to do with DC2 catalog and all these catalogs? Should we announce the...
You should, I mean, since it's a clusters analysis, I would imagine you have some connection with the cluster working group.
Yeah. Inside the cluster working group, we discussed this. I don't know if we should...
Should be a project. I think it's a good idea to announce it as a project, and so that other people can see it and participate if you want, and if they want, rather.
Okay.
Yeah.
Oh, great. Great.
So, but if you talk to, you know, Adam Manson, whoever, Camille, right? Camille is,
Yeah, we will discuss this. Camille is involved directly with this project that we started planning. So, great.
Okay.
Well, thank you very much.
Okay, any more questions? Then I have one question. So when you're adding all the galaxies and you're adding them, making sure you're preserving some properties, right, that you have from semi-analytical models or any different number of models. What about the cross correlation between those properties? Are those also being taken into account?
Okay, so this is actually discussed a little bit in the CosmoDC2 paper. The success of this method relies on the fact that the properties in the real universe really are correlated. We believe that they're correlated, right? The stellar mass, the star formation rate, the galaxy color, its brightness, these are all correlated. So we start with properties of stellar mass and star formation rate that are set by basically by an empirical universe machine model that somehow you think realistically on average gets those distributions correct. So you make a sample of galaxies that are more or less correctly distributed. And also there's a correlation in there with the halo mass because the universe machine gets the stellar to halo mass relation correct, more or less correct as well. So that's baked in statistically on average. Then the modeling of the rest frame, two colors and flux is conditioned on the stellar mass and the star formation rate. So there's a correlation baked in there again, but on the average distribution. And then you go off and you match those flux quantities with the Galacticus, the semi-analytic galaxies, and pick off the ones that have a good match. So, and you get the rest of the properties. So insofar as those the stellar mass, the rest frame magnitudes and rest frame colors of those Galacticus galaxies are correlated with the rest of the properties you get, you also get those for free. Is that making sense?
Yes.
Yeah, okay, so,
right.
So you are preserving some correlations on, I think, on average. And that's why you can expect, if you get those basic properties correctly distributed statistically, you can expect that the other ones will be correct statistically. But now, if you subsample the galaxies to finer and finer subsamples, it's not clear that things will look right. Because I'm not sure how well, Galacticus the semi-analytic model tries to do the physics from first principles, which it doesn't really succeed in doing completely, but it tries. And so how much is actually baked in is a little bit of an open question. But yeah, I don't know if does that answer the question? I think
yeah.
I think a lot of it is, on average, for the overall distributions, a lot is baked in. But if you start drilling down and trying to ask too finely, then since you're not doing things on a galaxy by galaxy basis, if you drill too finely, you may lose everything. You may lose that.
Right.
Yeah.
Okay. Any other questions? So I have another one then. When you showed us that when you were looking at the colors of the objects, that you made sure you had some red objects at high redshifts. especially because to make sure that the red mapper is detecting them. But then, I mean, that's a comparison between the distribution on the data and what you apply to the simulation. And my question is, would that make red mapper run better on the data than on the better on the simulation than on the actual data?
So what we were shooting for was that red mapper would work at all. When we first did this, because we didn't enhance the red sequence, in other words, we just statistically distributed the properties, the scatter on the red sequence for cluster members was just too big, right? Because we picked up the statistical scatter that's kind of there for field galaxies, and it was too much. And we iterated with Eli Rykhoff a number of times, and we needed to reduce the scatter, and so we reduced this scatter for the cluster members, and just kind of slowly turned it off for the lower mass galaxies. Now, he wasn't entirely happy with that, but that was the best we could do under the time constraints and modeling constraints that we had.
But you're also pushing to higher redshift. I mean, we do not know if there will be a well-defined red sequence at high redshift. I mean, I understand trying to minimize the scatter at a lower redshift, but as you go to higher redshift, the red sequence may not exist. It may fade away. So.
Yep, we don't know. So, you know, there are regions of parameter space that haven't been checked at all because we don't have data. Basically, you know, Andrew Heron, who was a lot of the architect of the empirical modeling, just with no data to guide him, he just extended something that he thought was, and there's no way to check it.
Fair enough.
Fair enough. Yeah, what can you do?
All right. Any more questions? Okay, so thank you everyone for coming. Thank you very much. It was a lovely seminar. And I guess I'll see you all next week when we'll have Pedro Bernardinelli talking about characterizing the outer solar system with dark energy survey. Okay, thank you.
Bye.
Bye.
Thanks.
Thank you. Bye-bye.
Bye.
Thank you. Bye-bye.